Já está.
It's a pleasure to be here today to present results from a long trip, 3 years of Bioecosys. I'm the first one of the session 2 of this afternoon. It will be a session for demonstration, and then we'll have the recent innovations. So, okay. So I will guide you regarding the first task of Bioecosys project. Okay. Thank you. Is regarding the ecosystem dynamics and indicators. So we have at the end of this first task several objectives regarding the assessment of ecosystem services in Val de Sousa case study area, update the ecosystem services products and services indicators using validated methodology that I will show you. Estimating the impact of forest management strategies on the provision of ecosystem services and guideline for the logical structure of the development of the resource capability model. We already talked about our case study area this morning by Jose. We have actually 360 forest owners in a joint management forest area that we call in Portuguese ZIF, and disregarding the Dori Souza and ZIF Paiva. And we have a forest owner, a forest association, a Val de Sousa Forest Association that is responsible for the development of the ZIF management plan. And why we choose this area? Of course, because we want to help the forest association and is representative of the Portuguese conditions, where we are talking about nearly 100% private ownerships, small scale stakeholders, poorly informed decision, and low impacts in silvicultural practices. And this is how it looks like our Val de Sousa. Here you can see that since 2012, they are about 43% of the total case study area burned. And you can see that along all the years what's happening. So this is one of our issues also in this case study area in Val de Sousa. So we are challenged to the need to update the inventory to reflect the current forest. When you look into the current forest management models, here you can see this map that is dominated by eucalyptus. We have the area inventory in 2004 and 2012 with 200 plots, and our previous inventory, it was in 2019, 158 plots. And we still have the eucalyptus that are dominating all the area. We have some pure stands of eucalyptus and mixed stands of eucalyptus with maiden pine. We have less areas with maiden pine, and somehow we have mostly chestnut from other broadleaves. So we find here and we bring us to that is necessary to think in the possibilities of alternative forest management models. And here is you can see that we are thinking on that and find the motivation related to the national forest policies, a stronger planting restriction on eucalyptus after the catastrophic fires in 2007. And we have also the actor analysis and stakeholders engagement, and several type of stakeholders, forest owners, municipality level, forest agencies, and they have a strong contribution and to the decision for the new alternative forest management model. So after all the workshops, questionnaires, and work developed by our colleague Marlene Marques in her PhD, we have we arrived to 4 alternative forest management model that we call 5, 6, 7, and 8. And it's pure maritime pine, pure pedunculate oak, pure cork oak, and riparian systems. So you can say that the Forest Owner Association want to explore this possibility of species conversions, and the alternative forest management model are in their planning exercise. So we start with the 4 current forest management models, and with workshops, actor analysis, research, we bring 4 additional alternative management models. And of course, the stakeholders are interested in supporting and regulating forest ecosystem services. So in our data and methods in this first task, we are using new inventory plots from the recent forest inventory, redefinition of 1,046 management units, 8 forest management models. You have the forest species, mountain pine, eucalypt, chestnut, purple oak, cork oak, and riparian trees. Forest grow and yield simulation have been applied. So we have several forest management alternative prescriptions, species reconversion, depending and according policy rules and species aptitude. Tree shrub cleaning periodicity have been, in this case, estimated and calculated. Regarding no-fill treatment, age 5 years and 10 years. We work at the beginning with 100 years from planning our period horizon with 10-year periods. And at the end, when we start in analyzing our results from the resource capability model, we also have done the same exercises with 15 years and 20 years to compare the results. And of course, provision of 7 ecosystem services. So this is a map where you can see here land use from Val de Sousa, and here we identify in this case, the green color is the forest area, and you have the pink color identifying in this case, where we have urban areas or houses. And this is a new, in this case, is a new land use and occupation for forest species. And you can see that the dark green is the pure eucalypt. So we still have a dominated eucalyptus species in the Val de Sousa. The forest management alternative prescription, this is, you can see at a glance that we have worked with the 8 forest management models. We have applied information we have regarding the ground yield models, and we have here somehow the information about it. So we have 7 that I've already told you before. We work with the assessment of 7 ecosystem services, wood production, non-wood production. We in the Bioecosys project, we estimated the cork, but we already have working with resin, and would be also for a future task. We have the biodiversity values, regulatory services with part of wildfire vulnerability, cultural services, carbon, and soil erosion. In this first task, we have already developed some methodology, and then we validated the methodology with the new inventory and the new management unit that we defined. So we can say that here, for the biodiversity management oriented indicator, we are using 2 things that are very important. We work with the tree species composition, and then we join the understory vegetation. And with that, we try to estimate the value. And we can say that the maximum score for the understory biodiversity refers, of course, to the highest availability of cover and habitat for wildlife. The methodology is already published, so you can read more about it, the methodology, but I can explain you at a glance what we have for all about diversity conservation. This indicator, biodiversity indicator score, increase with shrub cover and change with the tree composition and forest structure. So you can see at the green color, we already have values. It depends on the forest species. And it's important to have information about the age and the rotation, maximum rotation. And then we have another part of the biodiversity scores that is regarding the amount of forest following shrub cover. So here we are using a model we already have for biomass accumulation in Portugal, and you are calculated the biomass from the shrub cover. And then, of course, if you are talking about in this case, landscapes and different species, and of course, stand level with mixed species, you have here the proportion, the species proportion in each stand. Then we move on for the soil erosion. Regarding the soil erosion, and when we are talking about, in this case, when we are talking about forests, when you're talking about harvesting, thinnings, we want somehow that this kind of operation, forest operation, they will be include in the estimation of our soil erosion. So we started with the rules, we revised the universal soil loss equation that is published, and you know how well the equation from the literature, and we try to include a C factor, and our C factor here is dynamic. The C factor in the green color here refers to the cover management factor by different species, and this C factor is calculated and somehow is dynamic, and is calculating regarding different species. For each species, we have checked the literature, and you have different, in this case, equations that they will helping us to calculate the canopy cover of the species. So you can, in this case, see that if your C factor is dynamic, you can have the percentage of the coverage of your trees. And when you are doing a thinning or you are harvesting, you can see that your C factor will have a range of values and will be changing that value. So at the end, what we have a C factor reaches this maximum value when in this case, the canopy cover is equal to 0. So if you don't have anything, you have done a thinning or harvesting, a clear cut, and your C factor reach a maximum value, you can see that no vegetation protection and a high risk of erosion. But in the other side, if you had a minimum value for your C factor, so you can, in this case, is equal to 1, you have the soil, you can say that it's still covered by vegetation. And we have done several exercises with it and validated with after each operation, forest operation, and you can see the results and what happened when we shift from the species in the article that are published. For the wildfire resistance, we are using, in this case, a stand-specific wildfire resistance indicator, and is also published several years ago. And these bring three variables and that are very important. Is the probability, in this case, burn probability, the probability of mortality to occur, and the proportion of dead trees. And when we join this information, we are calculating the stand-specific wildfire resistance, and the next steps we are calculating, of course, for the landscapes. And you have a landscape fire vulnerability indicator ranging between 1 and 5. You have also we have in this case 2 articles published with the indicator for wildfire. The RALF index, when you are thinking in cultural services, it's somehow difficult to try to bring this information for a forest level. So here, what we need to include variables that are actually easy to use and understand for all the forest owners and so forest association. So in this case, you are using type of forest species, the impact of soil occupation. It's somehow a list of variables that you can use: the density, number of trees, visibility, stand age, even species diversity, and the RALPH index, recreational and aesthetic value of the forested landscape. You've used somehow 6 factors or concepts. And we can divide it by naturalness, standardship, complexity, visual scale, literacy, and ephemera. And then we'll have a class of RALPH index. We say very low for between 0 and 2, and very high between 0.8 and 1. But now you can ask me, okay, but and how can we distribute the information? Here you can see that you have the 6 concepts that I told you before: standardship, naturalness, complexity, visual scale, austerity, and ephemera. And I have a dimension. So I will give you an example on this case that I aligned the green one. For the complexity, we will have 3 dimensions: diversity, variety, and spatial pattern. For the diversity, we just need to analyze our landscape or management unit in this case and bring the information if you have 1, 2, 3, or more than 3 species. And for the variety, for example, you just need to look at that and say, do you have an even agent, two hedged, or uneven? And then we will average the information for the complexity, and we will have the same for the other concepts. It's an ongoing publication. In this case, we are working in the manuscript, quantitative approach to assess the impact of management practices on the provisional, recreational, and aesthetic services from forest and landscape. For the carbon assessments, in the methodology ongoing, we are using and calculating the estimation of carbon for biomass and wood ration references, and then we adapted for each of the species that I told you before that we are working, the current one and the alternative one. And this is the literature that we have been using. Some examples from the current forest management model and the alternative forest management model. You have here a landscape distribution. The current one only with the four forest species, and you have alternative one with all the possibilities that you have. Of course, regarding the aptitude and policy rules. And then now to analyze one of our ecosystem services. Here, regarding the wildfire, of vulnerability to wildfire, we have a business as usual for the current forest management model. And if you look at a new distribution with the alternative ones, you can see here a big difference. So we are answering actually, and you are trying to bring and achieve the goals that the forest owners and the association are looking for. And now I will tell you what we need and what we get in terms of ecosystem services landscape level. What can we do to meet demand, safeguard biodiversity, and reduce risks by modifying forest management models at landscape level, bringing together decision makers and ecosystem resource capability models. So at the end of the first task of Bioecosys, we can see that alternative forest management model regarding several, in this case, several ecosystem services, we can actually contribute to mitigate climate change, to make inroads in the national policy process planning, forest certification, and market payments for ecosystem services. Just to show you the demonstration sites we have for the implementation of the new alternative forest management model, Future Coke, maritime pine demonstration site and mixed oak. And you have the guidelines, and also in your folder that we distribute today, you have already this forest management model. This is the research team. Is the photo that I have with most of us, but it's a big team, that research team that have working on all these results. So I'm not the only author of the presentation, of course, but I'm here and now to talk about the resource capability models and how we can make a difference. So I will here in this slide, I will give the floor to my colleague Suzette to continue.
Presentation. A apresentação está aí ou não? Não. Good afternoon, everybody. Thank you, Brigitte. So I'm here as the responsible of the task 2 of Bioecosys project, and I will be presenting some work developed in this task, and let you know that I was not the only person working in this task. As Brigitte showed the picture, it was a team. Part of them are not here, but I want to thank them for that. And in the session, the next session in this workshop, the colleagues will present also work developed in this task too. But the intention of me being here, I will talk to you about the way we build Pareto Frontiers for ecosystem services, trade-off analysis in forest management planning. And this presentation, it will be presented by me, but it was also done with the colleague from University of Evra, Vladimir Bushenkov, that it's presented in here. So just a quick look what we want to answer in this task 2 of this project. We want to answer 2 big questions, that is how to combine spatial optimization integral programming with programs with Pareto Frontier approaches to analyze trade-offs between forest-based products and services that are measured per hectare basis and forest-based services that depend on the spatial distribution of the management options. This task is fed by the data that was produced and in task 1. So we received all the information from task 1, all the computations done, have all the ecosystem services, all the forest management alternatives, and built some. So we received the input data from task 1, so all the computations done and with all the ecosystem services and all the alternatives. These are the examples of the ecosystem services used. Then we, with all of this data, I want to tell you that it's a lot of data. So we simulated more than 85,000 prescriptions for this amount of stands, and we are still working on it to improve it, to add more ecosystem services, to add more possibilities to manage this forest. As Brigitte told you, the simulations were done for a 100-year periods, but then for the project, we decided that 100 years planning period, the planning horizon is very long. So for the stakeholder, it's very difficult to think in 1 century. So to know, well, how my forest will be in 100 years is very difficult. And when we did the exercise with a small planning horizon with 20 years, it was not enough to see the impact of the different alternatives on the provision of ecosystem services. So we decided, well, let's keep the 50-year planning horizon. So we already, it's long, it's still long, and we can measure the impact of our alternatives. So we built a linear programming model. So it's just to represent the complexity of it. It's very long, and of course, it contains all the information. So, of course, first of all, we did a LP model, linear programming model, with a single objective, just to check if I want to maximize one of my objectives, and also to identify if we keep managing the forest the way it is being managed now, how it will be in 50 years is the scenario that is in this table called max total timber. So the single objective was maximizing the wood production. And then we analyzed, well, let's see what happens to the ecosystem services if we change our objective function and see the impact on the others. But we are thinking only with a single objective. And when we are managing an area with a lot of stakeholders, as you see, they have more than one objective. So we have to think, not all of them want to maximize the revenues or timber production. Some of them may want to maximize or the fire resistance. Some others want to minimize erosion. So we have to think that we need to have more than one objective in our models. So with this, we worked with multi-criteria decision methods. So we use technique, a posteriori technique, build Pareto Frontiers. So we are presenting an iterative approach to generate the Pareto Frontiers of forest management planning problems, encompassing up to seven objectives. So we can think that we want to optimize not one, not two, but we can go up to 7. Of course, when we are optimizing with 7 objectives, it's more complex, takes a little bit more time, but we can do it. So the goal of this is to help the decision makers to assess the trade-offs between the objectives and set the levels of achievement that reflect their preferences. So it's the stakeholders that select where they want to be. So they don't have to to tell us in advance what are their preferences. We show them all the possibilities, and then they select their possibilities. So the Pareto Frontier is visualized in the form of decision maps that is arranged frontiers with multiple 2 criteria slices. So as you can see in the graph down with the 3 layers, we are using to generate this Pareto Frontiers, the feasible goal method interactive decision maps. Technique is used to provide interactive and animated visualization of Pareto Frontier generated by the estimation refinement method. In the end of this presentation, I will do a short demonstration of this tool for you to see how it is and how it works and all the potentialities that it has. So this is how the tool looks like. Here we list on this slide, sorry, some part of this program is in Portuguese, and it was done this way because the stakeholders are Portuguese, so it is in Portuguese. Here we select the objectives that we want to optimize. In this example, we are optimizing 4 objectives. So first one, it was maximizing carbon stock. Second one, minimizing soil erosion. Third one, we are maximizing fire resistance. And the fourth one, we are optimizing or maximizing biodiversity indicator. So, but we can, of course, as I told you, go up to 7 indicators and run this model. The other criteria are not optimized, but we can see the impact of the optimization of the 7, and we can see the impact on the other variables. This is how it looks like a Pareto frontier when we are looking to 2 criteria. So on your right, you have, on your left, you have a Pareto frontier when we are maximizing 2 criteria. So on the x-axis, you have carbon stock, and in y-axis, you have biodiversity. And of course, you cannot have the maximum of the 2. So that's why we have that curve. We have a compromise to have the maximum of one. We cannot have the maximum of the other. If that happens, we have all the area would be green. In the other graphic, I'm showing you how it looks like a Pareto frontier when we have 2 criteria also, but we are maximizing one and minimizing the other one. So this is how it looks like. But when we show you the tool, you will see how it is. So this is how it is represented, a Pareto frontier with 2 objectives. So let's add one more. The third objective will be added to this graph. So I added the third one, and the third one was maximizing fire resistance. And the third criteria is represented in colors. So each color represents one level of the third criteria. So the dark green will represent the highest level of fire resistance, the dark red, a lower level of fire resistance, and so on. So we can represent the 4th criteria. So we have another one. So here we are representing a 4th criteria. The 4th criteria is represented in rows. It can be represented in lines if you want to. So it's up to the user to decide how to see the Pareto frontier. We can also have, this is again with 4, but instead of seeing in rows, we add a scroll bar. And if we move the scroll bar, we see the Pareto frontiers changing, but we will see it later. So we prepared all this information with the LP models. We went to Porto. We had a meeting with the stakeholders. We met with them. We present them this tool. We have explained them how it works, how to read these Pareto frontiers, what is the information contained in it. So, and then we separate them in 3 groups according to their preferences. And in each room, in each group, they have selected the 3 baskets of ecosystem services that will be the ones that will be in the auction to be selected, to be sold.
And show next.
And that Miguel will show you. And I will show you a little bit. So just for curiosity, this is the Pareto frontiers that we presented to the stakeholders, and in one of the groups, they have selected the first bundle, the first basket of ecosystem services, and it was selected where that arrow, yellow arrow, is pointing. When they select a point in here, they selected the point, and then we can see how much they can have on the ecosystems that they were optimized. And as you can see in the table, we can also see the impact of this selection on the other ecosystem services. So we can see that we have that amount of carbon stock, erosion, fire resistance, and biodiversity, but we can also see what is the revenue that we will receive if we manage the forest this way, the amount of cork that we can extract from our landscape, and so on and so on. So I also added each point in the Pareto frontier will have associated a forest management plan. So when we select a point in the Pareto frontier, we will receive information like this saying in stand number 101, to have that amount of each ecosystem service as an example, in stand 101, you have to manage according to the prescription 503. Stand 1010, it will be, has to be managed with the same prescription and so on and so on. So we assign a prescription to every management unit, and we know if we assign that prescription to that management unit, in the end, we will have that amount, the amount of each ecosystem service. So this bundle, after getting the solution, we have the species composition of this bundle. As you can see, as you remember, Brigitte showed us that our landscape is mostly dominated by eucalyptus, and to have the bundle that was selected by these stakeholders, they have to change very much their landscape. And now, to have that amount, the selected amount of ecosystem service, you have to change their landscape. So we have to convert the existing species to new species. So this is how the species will be distributed in the landscape. And we also produce maps to see how the landscape will look like if we apply this management plan to have that amount of ecosystem services. So this is the bundle where the stakeholders selected bundle number 2. As you can see, they selected a different level of ecosystem services, so their preferences were different. Of course, the management plan to have this bundle will be completely different. This is where they have selected bundle number 3. So again, different levels of each ecosystem service. So just for curiosity, here is how the landscape will look like if we have bundle number 2. This is how it will look like if we have bundle number 3. So this information will be the one that will be an input for the task number 3 that Miguel will talk later. But in this example that we presented to the stakeholders, we used a simple linear programming, but we are working with ecosystem services that we cannot think them at the stand level. We have to think them in the landscape level, and some of them has to be think at the landscape level. So for this, we did a test instead of using linear programming, we did a test with integer programming. So we used the same case study area, but instead of using the planning horizon that we used in the example that had the task number 3, we used another one. So we used the 90-year planning horizon. We reduced the planning period to 3-year-old. So we have 30 planning periods, and we had the formulation. And this is just to show you that we can solve problems using integer formulation. Of course, the Pareto frontier, when we are using integer programming, it won't give us a continuous frontier. So the attainable sets in the objective space are not continuous. They are points, and they consist in a discrete point corresponding to a potentially large but finite number of feasible solutions. But this complicates a lot the problem. In this graph, I show you an example. When we have integer formulations, we have the solutions represented in points, and to have the Pareto frontier, real Pareto frontier, we have the frontier represented in the blue line. But to make the representation easy, what we do, we convexificate, we create the surrogate frontier, we do a convexification of this and create a Pareto frontier to be more easy to be read by the users. So we check the validity of this approach. So we build the Pareto frontiers, we select a point represented by Z with the red dots in the graph. we select some points in the surrogate Pareto Frontiers, and we checked where the real point, the real solution was, and to check how far we were from the real point. And the results showed to be good, so they were really close. So we explored this approach. But when we did this and when we convert the problem to an integer programming problem, well, it was really difficult to solve the problem for the whole area. So we had to decompose our case study. So we split the problem in 4. So we had to create 4 models for each sub-area and create the Pareto Frontiers. What is happening here? So we create one model for each sub-area. Why this is moving so fast? I'm sorry. So we have created one model to each sub-area. We have created the Pareto Frontiers for each sub-area. Here you can see one Pareto Frontier for one sub-area. Here are the results for the currency of our approach. As you can see, in 2 of our sub-problems, the maximum distance was less than 1%. So we can say that our approach seems to be, well, good. The way we represent Pareto Frontiers using integer programs. So these are the Pareto Frontiers for each sub-problem. And in each sub-problem, we select a point, so a solution for each sub-area. And with that, we can have the values of each criteria in each sub-area. And we can, with this information, with these Pareto Frontiers for each sub-problem, we can build the Pareto Frontier for the whole sub-area. That's what we are presenting here. So we have the Pareto Frontiers from each sub-area, and then with this we can build the Pareto Frontier for the whole area. And we get the similar results when we decompose the problem and when we have the full problem. In this exercise, we also did the specialization of the solution, so we can also visualize the solution of each sub-problem in a map, so we can see which operations are performed in each period, in each management unit, not only the harvests, but when we thin or when we harvest a stand, they are colored in the map. And we can also see the graphical representation of the solution retrieved from the point. So these studies are already published. Here you have 2 papers where we already published this work. If you want to learn more about this, here are the 2 papers that were recently published. So before the demonstration, I would just want to acknowledge the projects that funded all this work, especially Bioecosys project and all the others. And let's now move to the most interesting part, where you will see the tool that generates the Pareto Frontier working. So as I showed you before, so this is how the Pareto, the tool looks like when we open. It's not like actually like this. I already did part of our work. So when we open the tool, we have to upload our LP model, and then it will read the LP file, and it will list here all criteria that we have listed in the model. To be precise, I already create the Pareto Frontiers with 4 criteria, the ones that we have presented to the stakeholders. So in a real situation, we will need to generate the Pareto Frontiers. I will show you how it looks like, so we don't have to wait for the program to do it. So this is how the Pareto Frontier looks like. So this is how it looks like when we have two criteria, as I showed you before. So in here we are maximizing carbon stock. Here we are minimizing erosion. And as I mentioned, when we cannot have the maximum of carbon and the minimum of erosion, we would be here. And being here is not, we are not in the feasible area. So our solutions, they have to be here in the edge of our graph. So this is how we see a Pareto Frontier with two criteria. If we add the third one, as I mentioned, so let's select the third one to be fire resistance. It will add the third criteria. So it had the third criteria represented in colors. We can come here and change. So I don't want to see like this. I want to change. So we can come and change the way the Pareto Frontiers are displayed, and it represents the Pareto Frontiers in a different way. The way that it's more understandable for the user. So we can play with this and have it displayed the way we want. So let's add the fourth one. We can, as I mentioned, let's put it how it was. Let's add the fourth one. The fourth one, I choose to be represented in columns. So each column represents a level of the fourth ecosystem servant, that is biodiversity. So when we were negotiating with the stakeholders, we asked them which level of biodiversity you want to have. If they want to have this level, 3.3, this is the level of biodiversity that they want. So the Pareto Frontier that they have to analyze will be, of course, this one. But let me show you another way. I think it's more fun. So having the fourth criteria in a scroll bar. When the fourth criteria is in a scroll bar, if we change the levels of different level of the fourth criteria, you see I'm moving it, and you see how the Pareto Frontiers are changing. So this was the exercise that we have done with the stakeholders. This was a hard process. There were not a lot of people, but they had different objectives. So it was really hard to have them to say, I want that specific point. So let's do a small exercise here. So let's imagine that I want to have a highest level of biodiversity. You see what happens in the Pareto Frontiers? So all the other levels, so it means that a higher biodiversity will leave us with a lower fire resistance. See? So when I'm decreasing biodiversity, you see what is happening? The higher levels of fire resistance are showing up. So let's imagine, so I want to be with this level of biodiversity. And now let's define where I want to be in fire resistance. I want to have a more resistant landscape. Which color should I choose? Can anyone in the audience tell me? So dark red means lower resistance. This blue or green means higher resistance. So if I want to have a higher resistant landscape, I have to select my solution in this map. But this is very drastic. If I select this map, it's very drastic. See what happens in erosion. This is a compromise. So if we have this level of fire resistance, see what happens to erosion. We have higher erosion. So this is the difficult part of dealing with this amount of trade-offs. Is this, to getting a compromise. But let's imagine that we all got into a consensus and we selected this level of fire resistance, so well, let's select 3.9. So we want to select to have our solution in this level, in the dark green. So let's imagine that we want to select this level of carbon stock and that level of soil erosion. So we have to wait a little bit. This software, it will rerun the LP model, and hopefully it won't take long. So it's rerunning the model and assigning prescriptions to management units and computing all the criteria. And as you can see, that specific point that I have selected here has that level, that amount of carbon stock, that amount of soil erosion, the specific fire resistance that we have selected, and that amount of biodiversity. If we are happy with this, we keep this plan, we go to the model, to the program, and get the solution. We see the list of prescriptions assigned to each management unit to get this management plan. So I think it was more or less clear, and I think it looks, now looking at this, looks more easy to understand what I talked about. So if you have questions, I will answer you later. So now I will give the floor to Miguel and Cynthia. They will talk about the next task in this project that use the bundles that we have selected in the workshop that we held in Oporto.
Thank you, Brigitte. Good afternoon to everybody. My name is Miguel Sotomayor. My presentation will turn up in a moment, but just to save some time, my name is Miguel Sotomayor. I'm from Universidade Católica. Me and Alexandra Leitão, who is not here, and Cynthia. We are the team that work together very close to the rest of the team from Porto on the end line of this production line, on the trying to think about the way to get funding for these forest ecosystems that this Pareto Frontier showed to the stakeholders. Okay, so the idea of my presentation, this will be developed, as you see, in two parts. But first, I want to explain you the rationale of using auctions to get funding to the forest owners to produce to supply more of no-market forest ecosystem services. And then I'll present you what is the Ecocell platform. This is another of our objectives of this task of the project, to develop a tool to allow to get funding through auctions to forest ecosystem service bundles. So I'll explain shortly what is the Ecocell and its origin now, and what is it for. And then I'll get you a few conclusions, very brief, of our work so far, and what is still needed to be done in the future. And then I'll pass to Cynthia, who will show you how the Ecocell auctioning platform works in a mock auction, but a real one with people bidding for 3 alternative forest ecosystems bundles. Okay, this is what I'm going to do, what we are going to do. And concerning the rationale of using auctions as a way, a complementary way, a novel way, at least in Portugal, to fund non-market for forest ecosystem services. The idea behind is forest owners, in his business as usual decisions, complying with all the laws and regulations, might not supply enough quantity as the society wants for non-market forest ecosystem services. Why? Obviously, because they are there to get income for them and for their family, and this might not be the way they maximize that income, that welfare through income. So in order for them to be on all the compulsory laws and regulations to supply more forest ecosystem services, they would have to be compensated, financially compensated. And one possibility of getting that funding is by something that is similar but not exactly a system of crowdfunding, to get people by means of auction, stakeholders, people demanding those services not enoughly supplied, to bid for their favorite alternative forest ecosystems bundles. And the auction is successful when at least one of the bundles on offer gets a sum of bids that is at least equal or higher than the compensation, what we call the reserve prices, the forest owners want in order to be willing to adopt the management plan to produce that bundle. Of course, the rationale for this sort of auctions is people participating in the auction and bidding non-winning bundles will be refunded. The others, betting in the right ones that will win the auction, will not be refunded, but they will benefit from a contract between them and the forest owners to decide for that management plan and implement that management plan and produce in time the bundle that was demanded by the bidders participants. And this would mean a contract, as I said, for a period of time that might, Suzette also discussed this issue of the length of the contract, from anywhere from between to 50 years to make it reasonable for the bidders. Okay, the whole view of this procedure. First, we have this should be the object of this procedure should be a forest area, a forest landscape area, where we have a problem of the provision of ecosystem services does not fit what stakeholders for that area or society wants. So, and why is nothing illegal? Simply because the forest owners in their business as usual decide for a management plan that is the best option for them. And if there is a difference, so there is space to get solutions through these sort of auctions. And then what we should have, so we profit a lot from the work from the other tasks you just heard about. So the Pareto Frontier they build is fundamental for this procedure because we can take that tool and put it in use with stakeholders and then and let them choose what are their favorite ecosystems bundles concerning especially the provision of and the provide non-market forest ecosystem services. Okay, so once we get 2 or 3 or 4 alternatives to business as usual favored by the stakeholders, then we are in the conditions and also we need to calculate for each of them the reserve prices, which means how much for each one the forest owners would need to be as a compensation to be willing to adopt that management plan, then we can auction them. So, and we can auction them. It's a web-based platform, as we see. So when anyone who wants to contribute to his favorite basket or bundle of forest ecosystem services can be anywhere in the world because it's a web-based auction. So if there is one bundle in the end that wins the auction, it means that bundle have to collect a sum of bids higher than the reserve prices, equal or higher, and is the one fulfilling that requirement that has a higher surplus. So this will be the winner. In that case, this will be followed by a contract between the forest owners and the bidders that bid for that winning bundle. This is the whole story. And so you might be curious, in our case study, what non-market forest ecosystem service have been, were included in the auction bundles: carbon stock, biodiversity, soil erosion protection, and wildfire resistance. Okay, what is Ecocell? Ecocell, as I said, is a web-based auction platform. It was first developed by the team of the University of Washington. One of the team members, I think the leading team member, was Shandar Toz, you heard this morning. And our task, part of our task was to adapt it to an European context, to be used in Europe. This was our job. The Ecocell, what does Ecocell do? They said from the scratch, from the designing part to the auction itself, this Ecocell platform helps us to set entire auctions. Using, they call each auction for a particular forest area a land campaign. What is the advantages of doing these sort of auctions in the web? Because it allows easy access to the auction, less barriers for people who are interested to contribute to their favorite bundle. Of course, also it highly facilitates all the logistic of organizing our auction. So we did it in a classroom, a computer's lab, and afterwards in the web, and it is much easier, and it might involve much more people. This was already said. Okay, what sort of information is given to the bidders in an auction, a forest ecosystem service bundles auctions? First, we give them, as you will see, a comparative chart comparing the business as usual bundle of ecosystem services with each of the alternative bundles, the ones that are supposed to provide more non-market forest ecosystem services. And secondly, we give them maps, geographical maps of the forest area with the species distribution, both for the business as usual situation as compared to one of the alternatives of non-market forest ecosystem bundles. And finally, we give them the chart showing not only this same distribution of species for both as compared to each of the alternative bundle, but also pictures to show them the sort of landscape we would get for each of the alternative forest ecosystems bundles. Okay, so we did this, we test after developing the European version in Portuguese. We tested twice, one, as I said, in a computer's lab with 10 stakeholders and for 4 forest ecosystem alternative bundles selected by Pareto Frontiers by the specialists, very contrasting. And for that case, we got one winning the auction. And then we did a second test, and we played a little with the budget for the bidders. And for that second experience, which was completely online, we get a little bit more stakeholders participating, 18, and for this case, we didn't get any winning bundle. Okay, after these two experiences, what we realized so far, and this still needs probing, but first, we found that all the participants in the auctions were very enthusiastic about, I think they felt it as a sort of a game after an initial period, very short period of understanding how it works. Then they were very enthusiastic and also very dynamic in communicating. We let them communicating with each other in order to promote their favorite bundle. And about the platform, so Ecocell show itself as user-friendly for a very varied sample of stakeholders. Another aspect that we identified that needs probing is crucial, the way we present the information and the amount of information, because we felt that they use mostly the short descriptions we gave them about the bundles, rather than the more detailed information we also gave them. And also we noticed that these auctions get settled, so with a winning or non-winning, anyway, in a very short time. We thought it would take more time, the dynamics, to get a winner, but in less than 25 minutes, the results are settled totally. Okay, some more information. We noticed that I think this is very detailed, and I think you profit better if we go quickly to the demonstration. But the idea here is we got some information how to more efficiently organize the auction in terms of getting a winning bundle. So this was already said by Suzette about the long contracting spans that we felt that might cool down bidders' demand, because they might say, oh, 100 years is too much, or 50 years, so I will not be here, so why to bid for this bundle? So this is a problem we have to deal in the future. And also another crucial problem is the way how correctly we calculate the reserve prices. We, from the economics point of view, compared to the forest people, we think they were over assessed because they didn't count. So this is an issue that should be, and this is crucial because the higher is the reserve price, the higher the needed compensation, the less likely to be successful the auction. And we have to have real compensations that the forest owners want. Okay. Most important points here, bidders' trust regarding implementation also in contracts. That's something that puzzles the bidders. What type of contracts will we get? How can we trust that these contracts will be reinforced? This is an issue. It might also make them less trusty in the process. And the thing of the information we give and the way we give also have to be studied. And the last point before I gave the word to Cynthia, a big problem. If the compensation price, even if they are completely right, are very high as compared to the budget the stakeholders want to invest, so we will not ever get a winning bundle. So this method does not fit every situation. Okay, so Cynthia,
okay,
up to you.
yeah. So I'm going to share the screen now. camera. Yeah. Okay, so, well, I'm going to do a very brief demonstration of the platform as we got it. This is kind of the condition of the platform as we got it. This is the landing site. So what we should do, like what is the purpose? The purpose is that this platform should be a dissemination tool for both landowners and bidders. In this case, let's call it like I will act as a bidder. I would show you. So yeah, I designed this mock auction especially for today. So I have asked some colleagues present here and as well as others join remotely to participate as bidders in this auction. So I'm going to show you how this in like 10 minutes, how it should work for like, let's say like a day or two, or maybe some hour or half an hour. So this is the project, like this is the land campaign that, as Professor Sotomayor said, is how the platform and the Ecocell system calls the auction itself or the auction project. So we find in the first, after the landing site, we find this general page that is a very, it's a joint effort with this team where they produce the maps and then we got this chart that this page has the purpose of offering the bidder, the potential bidder, all the information that we think they may need to assess first their interest in the project, and then specifically which kind of which of the bundles, in this case these three bundles that by the way were the bundles that they choose in the experiment, so are, let's say, like real cases, at least real preferences of a group of stakeholders. So they can just, let's say, go to bundle number 2, which will offer specific information of the bundles. So they can assess where, like, which kind of ecosystem service this bundle maximizes or prioritizes. Then the implementation maps of this specific bundle, and this chart that also presents some photos of the distribution of the species in case of this management plan being implemented. So how this works? Once the potential bidder logs in and is interested, let's say we are interested in this platform, we go to bid on this option, and I can bid, for example, I don't know if my user has still 10 euros. So starting now, let's go. And I will ask, please, my colleagues that are going to bid to do it starting now. I can go to the land campaign, and we can see the campaign status. Here. So how this works? I just bid 10 euros here. So we can monitor live as we are talking now. We can monitor how the users join and bid. I have decided, and we as owners of the land campaign can decide the top budget, if it is disclosed or not, if the reserve prices are disclosed or not. So these kind of variables are interesting for us as researchers to manage, because it may influence or not the decision. So we can see this. It's very interesting. Like I would close the. You see, it gets updated. I would close this in 5 minutes as we talk, and I don't know if we are going to reach a reserve price, but the idea is that it does. Like it happens, and we can also monitor the activity of the users. An important and interesting feature of the platform is that allows the owner of the auction to create users. I create users for this campaign, and I distributed to most of the participants. I have a personal username, and of course Harold has one, and he joined and bid one. But if I wish I could create usernames, like anonymous usernames, so they, even between themselves, are not able to differentiate who is bidding for which bundle or not. So in terms of information and communication management, this platform also gives us a lot of interesting tools to manage. So I created around 20 users, something. I don't know if all of them are going to join, but I expect, I am seeing that some of them are already working on it. So, and then this is public information, by the way. I am showing a site that is able to be consulted live by any of the bidders. So it's also for them a tool to understand how their bids and how their offers are influencing the auction. They are able, if I wish to, they are able to withdraw their offer and put it in another bundle. They are able to redistribute their money, like they can bid, for example, I put 50 euros as a top budget, so they can put 10 euros in one and 30 in another because of personal preferences. Maybe it's another topic for that, but they can do that. And for them to be able to monitor live the evolution of the auction with this chart, it's a very important information. So from the administrator's perspective, I do have another feature that it's just an extra button here, that it allows me to download this activity, but from the beginning. This is only the latest activity, shows the last 4 movements, like to say it like that. But I can download the whole activity since the first user put 1 euro or something until I decide to close it. So that is also an interesting feature because it allows us to understand maybe the interactions. We can count, like in a real case scenario, that this may motivate people to do some lobbying or some real campaign. You know, if someone is very motivated to see their bundle come true, they can, you know, do some dissemination, some communication, strategic communication work. We actually saw that happen in the workshop. The landowners, once they understand the concepts that Brigitte and Suzette explained with the Pareto Frontier and everything, we saw them change preferences and they withdraw the offers that they had already done for one bundle and they put in another. So we had first one winning bundle and then we end up having another winning bundle. So it is a very interesting social experiment. So let's see, we are kind of going up now. So let's wait like 4 more minutes and I will close it and we see how it goes. So as the users keep bidding or deciding their bids, we can also see, for example, in land campaigns. This is the only land campaign that it's available because I made it look like that for demonstration purposes. But of course, we can find here a lot of other land campaigns. It makes sense to have one land campaign per area, of course, because we can only implement one management plan simultaneously. Also, we have this latest activity chart in the landing site of the land campaign or auction or project areas. We are same words. I work for the same concept that is the auction project. And something interesting, we are also able to see how we are managing our offers per land campaign. So in this case, I have bid only 10 euros for the bundle number 2, and I have still 40 euros to bid if I want to. If I don't want to, I just don't. If my bundle doesn't win, then I get back my 10 euros. And if it does win, then I don't, of course. So yeah, we can check the campaign status a bit more. each bundle site has the same chart, the same comparative chart, only probably makes a point on the specific chart of the specific columns of the bundle. But it's basically some information that we consider that it is the information that should be the motivating one, but this is still a field pending to be explored, of course, like what does really makes the deal breaker for the bidders is something that we can just begin to understand. Let's see the campaign status. Well, yeah, Harald is doing some business. So it is very interesting how this is interactive.
You see my point that if there are not enough people willing to pay for a particular non-market forest ecosystem services, no result, no change will occur.
Yeah.
In this case, our guest bidders were not very active, or some missed the invitation.
Things that these prices, for example, these reserve prices that we have, like for example, all of them more than 600 euros, like those are of course re-escalated prices. Like we did the math to. We were thinking about a group of between 30 and 40 people for this experimental purpose, but real reserve prices are much higher. So,
but one of the interesting things of this is that bidders seeing that their favorite bundle is getting very low bids, to avoid another that they don't want at all, they might change strategically and start to bid in their second favorite. And these dynamics reach a more efficient result as compared to just one possibility being offered.
so 1 minute more and I will close it. So of course I will close it manually, but then the idea is that this also allows me to close it, to set the opening and close it dates, because it's actually what makes sense. So I will just close it now.
Okay, from our part is.
Yeah, but it is.
About the idea, if you have any questions, together with questions to the colleagues, so we are here to answer you according to our experience of testing this tool.
Yeah, no winning bundle.
Thank you.
Thank you.
We will keep the questions for the Q&A section. So we are just changing seats. You ask the next presenters in the following session to come to the table, please. Sorry for the noise. Onde quiser.
Hello, I'm Eduardo Eloy, and I'll. Thank you. Hello, I'm Eduardo Eloy, and I'll be presenting this project, a constraint modeling approach for forest management. So we've already seen the Val de Sousa forest in northern Portugal. What's important here is that it's divided into 1,373 management units, which I'll refer to as MUs, and we're tasked with managing the forest throughout 90 years. Managing it means assigning a prescription to each management unit. We've already heard of the prescriptions. You can see an example here. There are sets of actions to take throughout the 90 years. So it may tell us to thin the branches in the trees of that management unit, to harvest, so cut down all the trees, or to do nothing. And it tells us how much wood each of those actions give us. But there's a limit. To prevent soil erosion, the contiguous amount of forest area that can be harvested in any given year cannot be above 50 hectares. So for example, if we have 30 hectares in one side of the forest and 30 hectares in the other, and we harvest both of them in that same year, that's valid. But if they're closer together or adjacent to each other, and there's another MU unifying them that's also being harvested, they can't be harvested in that same year because that would be more than 50 hectares. So this is a constraint optimization problem. There's a relation between the prescriptions which are applied to each MU and the amount of forest area that's harvested continuously. And there's also a relation between the prescriptions which are applied and the total amount of wood that is yielded at the end. And that's what we can optimize, the total amount of wood. So we chose to implement this in the Shoko solver constraint programming framework of the Java language. And it sort of was like this. We use a constraint variable array to represent the whole forest. And these arrays have constraint variables which differ from normal variables in that they're not initialized with the value, but with a domain of possible values. And each index in this array represents an MU, a management unit. And the domain of possible values in that index represents the possible prescriptions values that can be applied to that MU, and they're all different. So the prescriptions are relative to each MU. We also use another constraint variable array to represent the wood yielded by applying a prescription to each MU. So then we iterate through all the MUs in the forest, and we create the constraint that enforces the 50 hectare limit by passing through a custom propagator DMU, which we are iterating through, and the whole forest, the information about the whole forest. Then once that's enforced, we say that, okay, so whatever prescription was applied to that MU, the wood that prescription yields gets added to the wood yields array. So the custom propagator works by iterating. So the custom propagator is checking all the possible values for that MU, so for the prescriptions, and in whichever one it is currently on, to check if it's valid, it iterates through the years in which it has harvest actions, because those are the only actions that can break that constraint. And in all of those years, it has to check if they're valid by checking if the adjacent MUs to this MU are also being harvested, and if the ones adjacent to them are also being harvested, or if they're not, and if that doesn't break the 50 hectare constraint. So it passes to the glade propagate function, which is a recursive function, the year in which we are currently on, the MU in which we are starting from, and the integer 0, which is an accumulator. And like I said, this glade propagate will add the area of the MU which we know is being harvested to the sum, which starts at 0. If at any point this sum exceeds 50, so 50 hectares, we throw an exception, which is caught back here, and the fails function is called, which in Choco, it means that the propagator knows that these values aren't valid and has to try different ones. If the limit isn't surpassed, then we still have to check the MUs adjacent to this MU. And if they have cuts, this keeps going. If at any point the limit breaks, we could throw an exception. If not, at some point it ends, and so the solutions are valid. So what are the results? When using this with the full input, so the 1,373 MUs, it doesn't find a solution. The problem is too complex. So so to better analyze this, we can limit the input and see what's going on. One of the ways in which you can do this is by only working with the MUs that are within a certain distance from an arbitrary MU, which we pick at the start. In this map you see here, we're picking the MU with the ID 0, which is the first MU that comes from the input, and which should be around there in the pink region, because it spreads out in the circle, the distance. And when we do this, starting from a 1 kilometer distance up to 4 kilometers, the execution finishes quickly and finds a solution for each of these MUs. From 5 kilometers on to 7 kilometers, it's not finding a solution, but it does finish. And at 7 kilometers, which is what you see on the map, it's already taking more than now. By 8 kilometers, it's not finishing execution, it's staying there for too long. I've noticed that at this point, we're already dealing with that green region, which is Penafiel, which is the most problematic region. Something I forgot to mention is about the optimization process. So once we actually leave this loop, the wood yields array, each one of its indexes already has the proper constraints applied to it. So once the solving process is done, the wood yielded by applying the prescription to each MU is already on this array. So to optimize and maximize the wood yielded, we tell Choco that it should, we tell the solver to maximize the sum of the contents of this array, which by the end already have all the wood yielded by applying the prescriptions to the MUs. The other way we can limit the input, besides by distance, is checking solutions by region. So there are 4 regions. There's Paredes in blue, Penafiel in green, Paiva Norte in pink, and Paiva Sul in light red. For Paredes and Paiva Norte, the program, we can set the limit to 50 hectares, and it finds solutions in relatively quickly, which can yield more than 1,000 tons of wood. But once we get to Paiva Sul, we actually have to increase the limits to 81 hectares, which isn't legal. It has to be 50 hectares, but with this, it does find a solution relatively quickly. We can see here that in Paiva Sul, we're already dealing with more MUs which are large, which are above 40 hectares, which tend to spoil a lot of solutions, because that's where it's more likely that the 50 hectare limit might be broken. It's when those MUs have to be harvested. So a lot of solutions where these MUs are harvested in the same year, or these MUs and MUs around them are harvested in the same year, have to be thrown out because they might break the constraint. Whereas if they weren't there, the solution might be found and no problem. So before we move on to Penafiel, we actually tested checking for solutions for the Paredes region and both Paivas at the same time with 50 hectares, and it does find a solution, though it's after a long time, after 13 to 14 hours. And I've noticed that since the Paredes region is completely separated from Paiva Norte and Paiva Sul, here it's really just the solution for Paredes is the same as the previous one. but for Paiva Norte and Paiva Sul, it is different. Penafiel, finally, which is the most complicated region, has a lot of MUs which are very large. 3 of these MUs are even 49 hectares. So not only can't they can't be harvested when they're adjacent next to each other, but probably nothing can be harvested around them in that same year when they're being harvested. And as you can see, near the top right there of Penafiel, a lot of them are actually so clustered together, which is a difficult situation. And we have to increase the limits all the way to 96 hectares for it to find a solution relatively quickly. So something that can be done here, which we didn't do, is breaking up these very large MUs into smaller MUs, which are more manageable and have different prescriptions that can be possible to apply to them so that this doesn't happen. This is just something quick. We tried to, we checked if increasing the limits would also obviously increase the amount of wood yielded by maximizing the solution. And we can see that it does, although at some point it tends to plateau regardless of how much we increase it. Just a note in the paper, I accidentally labeled this unit of measurement as tons instead of kilograms, but that's wrong. It is kilograms. So the conclusions, we proved that the problem can be modeled as a constraint optimization problem. We contributed this new global constraint that can ensure that every MU can be continuously affected by an action. In this case, it was the harvest action. Could have also been analogously the thinning action. We contributed an implementation which is functional but limited due to the complexity of the problem, as I explained, and an implementation that compares well with a paper from 2008, which I think the authors are here, that was based on mixed integer linear programming. As for the future, we plan to use meta-heuristic solvers like local search and solvers that allow for parallel programming, which we expect to be a factor in increasing the performance of this type of constraint programming, which we expected to have in Choco Solver, but it didn't work quite like we expected. And this will be the work of my master's thesis. And thank you, I'm done.
Como é que seleciona?
Eles comparam.
I have to point to that.
É aquilo.
Isabel, é esse?
É isso.
Okay. The first slide is the proposal. Okay. So I'm going to talk about this problem, optimizing data scheduling. Good afternoon. Sorry. I have to point to that.
Ela não está a passar. Não.
Não está passando. Okay. No. So I'm going to talk about this problem, optimizing harvest scheduling with environmental concerns in a multiple harvest context. This is a joint work with Suzette, Marlene, and Marco. I hope to talk about these 5 points in 5 minutes. The forestry problem that we have been studied is the following. We would like to manage the forests, factoring the production over a temporal horizon of 100 years. I have to say that we worked with the first data before the big fire, with multiple harvests in each stand, subject to a regular flow of timber harvesting, where each clear cut cannot exceed a given size. All you know the disadvantages of having large clear cut sizes. They have an impact on erosion, water quality, wildlife, security, among others. If you, this is a solution that we have obtained with a formulation for this problem, but with no clear-cut constraints. And as you see, in period 5, we discretized the planning horizon in 10 periods. In period 5, for example, we have here large clear cuts to large. So about the data, it's we have a highly combinatorial instance. We have 10 periods. This number of prescriptions for Castelo 5 and Inicial Paredes. We have we have a large number of prescriptions per stand in average. We have a large number of harvests per prescription in average as well. And we have the area of the stands is in general small. The large, we have, so because of this, we have in average a large number of stands per clear cut. So we have here extremely complex search phase. But even so, we are interested in approaches that measure the solution's quality. So in the literature, we have a lot of several formulations. Most of them are concerned with these kind of problems, but with only a single harvest at most for each stand. We have here this last flow formulation by Yoshimoto, but this is a formulation for multiple harvests per stand, but is not suitable for this case. The other formulations can be adapted for our case, of course, but some authors of these papers concluded that if we, for example, for the path formulation, we use a technique that generate for the constraints when they are needed, or for example, the cluster formulation, when if you generate the variables when they are needed, not at the beginning, these formulations work better for large instances. We worked with, I have to say that we worked with a computer with 8 gigabytes With this research, we decided to follow these ideas from some of these papers, and we decided to start with the path formulation, where the variables of the path formulation are these ones, but we decided not to use all the the path formulation has several constraints, but the problematic constraints are these ones that we have here at the bottom of the slide. They can be extremely, the number of these constraints can be extremely large. So we decided to not to use all these constraints a priori. So we implemented a branch and cut. The branch and cut starts only with the other constraints. And these constraints are generated when they are needed. So this is the algorithm. We generate path constraints. Not all, they are, the number of these constraints are so large that even if they are needed, we generate only up to a given number of constraints. And we obtained the results. Sorry. After 2 hours, we obtained an infeasible solution, but this infeasible solution has only a small number of infeasible clear cuts per period, and the number of stands in infeasible clear cuts over the planning horizon is not so large as that. So what we decided after this time, we decided to we save the solution that is feasible, and we decided with these infeasible clear cuts, we decided to implement a formulation that is polynomial in the number of constraints and variables, the bucket formulation, and we applied a branch and bound with simplex for the set of stands that are in infeasible clear cuts. So in the first step, we applied a branch and cut, where the path constraints, the difficult constraints, are generated when they are needed, and after a certain limit of time, we applied a branch and bound, an enumeration technique of integer solutions with this polynomial, this formulation that is polynomial in terms of number of constraints and variables. And this procedure provides a measure of the solution quality. And the computational results are these ones. For CP, Castell-Paiva, we obtained a gap of 6.1%, and for Penafiel-Paredes, a gap of 3.5%. If we put a limit of time for the second step in 10 hours, the gap of the obtained for Penafiel-Paredes was the same, but for Castell-Paiva, the gap decreased. Here we have the solution for period 1, 3, 7, and 10. And we can see clear cuts, smaller clear cuts than before. About the climate constraints, we inserted only constraints on the volume, not for each species, but for the whole species. Here the red curve. We used 20%, the maximum allowed variation, and but we can see that although we inserted constraints on the volume for the whole species, we can see an even flow for each species as well. This is for Castel Paiva, and this is for Penafiel Paredes. This is about the net present value. You can see a peak in the second period, but this is related with the prescriptions for eucalyptus that have at the final period 1 harvest. Yeah. And conclusion. So this work presents an approach that measures the quality of the solutions. Although we tried at the beginning to solve the problem for the entire forest, for Penafiel Paredes and Castel de Paiva. We split up the region in two regions, but if you want to consider the volume constraints link the whole region. So an optimal solution for the separated regions might not be an optimal solution for the entire region. So although the problem cannot be solved for the entire forest by using this approach, good solutions are obtained for the two regions. Of course, we would like to decrease our gap. I think the first step that we want to follow is to increase the memory capacity of our computer. So I finished, and thank you very much.
Mas eu quero pôr. So, this presentation is about a forest network design and optimization. Can I? This is a joint work with my colleagues Miguel Constantino, Suzette, Sebor, Marlene, and Marco. The outline, we are going to present two solutions approach. I present the first one and Miguel the second one. So, one of the main challenge in forest management is the design of a forest road that allows the transportation of timber from the management units being harvest. Management units, it's what we call two stands, I call two stands. So we want to transport timber from management units being harvested to the main roads and to the sawmills and pulp factories. We are going to address, our case study is only the Paiva zone. We know harvesting scheduling plan. It covers a time horizon of 10 periods, each period 10 years. So in each period, we have to decide which forest roads to build or maintain, and to define the timber flow in these forest roads so as to join the management units to the main roads and then to the factories. The objective is to minimize the associated costs, road building and maintenance costs, timber loading costs, and timber transportation costs. The first step is to obtain a good representation of the case study, the zone that corresponding to the case study. So we use GIS information, and we assumed that timber was forward to the boundary of each management unit. Okay, so loading will occur in the boundary, and the trucks will travel along the boundaries of the management units. So to describe the boundaries, we cover the boundaries with vertex, the green vertex, and with edge linking adjacent vertex. The green vertex are the potential loading sites, timber loading sites. Then we have to also consider, we have to know where are the exit points of the forest. And so the purple lines correspond to the existing, the main roads, the national, municipal, the pre-existing roads. And with this, we assume that the exit points of the forests occur in the intersection of these main roads with the boundary of the management units. And so we have the purple vertex, which are the exit road vertex. The objective is to reach one of these vertices, okay? So next slide, we show an example of a solution in a specific period. You can see the orange triangles are loading sites with timber, and they are linked, the triangles are linked to a purple vertex, yeah? And they are linked by blue and orange segment lines, which correspond to forest segment roads. The blue lines correspond to segment roads that are maintained in this period. It means that they were built in the previous period. And the orange line correspond to segment roads that were built in this period. To solve the problem, we propose a mixed integer linear programming model that includes 3 types of decision variable. Decision variable, binary decision variable that are related to the decision of building or not building the W variables, segment road in period T, the Y variables that are related with the decision of maintaining segment road IJ in period T or not. We also have timber flow continuous variables that account for the amount of timber that flows in a segment IJ. In the light gray, we have the model. We just highlight a set of constraints that cause some drawbacks while solving this model with the commercial solver. This set of constraints, which relates the 3 types of variables, ensure that timber flow only occurs in a segment road that was already built or maintained in that period, okay? And it includes a parameter M, a big M, usually, they are usually called big M constraints. It includes parameter M, which should be estimated by the user. And possible estimate for this parameter is to assign the amount of timber harvested in each period. But this is edge value, and including this set of constraints in the model with is this edge value, and solving the model with a branch and bound, with a commercial solver like CPREX or XPress, leads to high CPU times to obtain the optimal solution, or even to only obtain feasible solutions. So we propose a heuristic approach to give alternative to the estimates of this big M. The first approach is composed by two models. So we receive as input GIS information and the harvesting plan, and we build the potential forest road network. Then this is the input for the second model, which is a heuristic solver. And the heuristic solver iterates between estimation procedure that gives estimates for the big M's. Then we solve the resulting MILP model by a branch and bound with a CPLEX or XPress. And since this estimation procedure is based on a clustering algorithm, we can change some clustering parameters to obtain new sets of estimates, solve again, and so on. We can iterate between these two procedures and obtain a pool of feasible solutions for the problem and choose the best one. The main idea of the estimation procedure is that we noticed that there are two types of management units. Management units that include exit road vertex on their boundaries, and management units that do not include these exit road vertex, and so they should reach this exit vertex. Concerning management units with exit vertices, we noticed that timber loading usually occurs near this vertex, avoiding extra costs on building the roads, maintaining and transportation timber. So our concern goes to management units without exit road vertex. And we propose to make cluster of such management units. For example, in this case, we can consider 3 clusters based on the shortest path to exit vertex. And instead of, if, for example, in period T, we have timber to transport in management 1 or 2 or 4 or 6, we can estimate M by the maximum of the amount of timber in each cluster instead of the amount of timber that is produced on that period. So we reduce the value of big M's, and we obtain solutions that are within 3% with the 3% of gap. So now, Miguel.
So allow everybody, so now we change.
And this work has already been published in this paper.
Thank you. I'm talking about improving the mixed integer programming model. And as Marta said, the big problem of the previous model, or the model that you are trying, are these big M coupling constraints. Because linear, the LP bounds are very weak. This is because when we try to solve the linear relaxation, these constraints can be satisfied since the M is very large, can be satisfied with very small W or Y variables. So that's why the LP relaxation is very bad. And after 24 hours running this model, we end up with more than 7% gap, which is quite a lot if you are talking about more than 2 million euros as an objective function cost. See?
Yes.
Oh, okay. So one idea to improve this mixed integer programming model is just to try to have a better linear relaxation. And one way, one standard way to do this is, for instance, to add an extra index to the variables. And in this case, we add an index that stands for the origin of the timber. So you have an extra index U, which is the management unit from where the timber comes, the timber that flows in edge IJ. What do we gain with this? Is that because instead of having a big M, now we can put a small m in the constraints. And this value is, since the constraint is for a specific origin, management unit of origin, you can have the production from unit U in parity. So after these constraints give very tight LP bounds, but there is a big problem here, is the number of variables. Because in this Python instance, you have more than 1,000 management units. So we have to multiply the previous number of variables by 1,000. So you end up with 130 million of variables. And of course, you cannot solve such a problem. It's impossible. So what next step is try to reduce the number of variables. And there is a very easy way to do it. If you look at this picture, IJ is an edge segment that you want to send flow, send timber from it to build or maintain and send timber. And U, there is a management in it. And if you observe, there is no way that you can build forest roads from U to I or J that does not cross one of these national roads. So if you are it's not interesting to build such a road because you are going to send the wood to the first point, I mean that this forest road meets the national road. So all these variables can be discarded from the problem, and you only have for these specific edge IJ, you only are going to use management units from this green area. And after doing this, we end up with only 8 million variables. Seems a lot, but after putting some additional more variables, but very few variables and constraints to strengthen further the formulation, we were able to solve the problem in less than 30 minutes to obtain the optimal solution of this problem. And why is so? Because actually the linear relaxation is integer here. So the formulation is really very tight. And we could solve the problem with the linear relaxation. So this 30 minutes to solve a linear programming, not an integer programming. Actually, if you want to solve only the linear programming, it's less time because we try to solve the integer programming. The solver has a lot of heuristics. We try to do some things and takes 30 minutes. If it is only linear programming, it's 20 minutes. But we need a 32 gigabyte computer. With 16 gigabyte, we were not able to solve it. So we are happy, but we are not satisfied. And why not? Because 8 million variables is still a lot. And in the next step, we want to add decision variables on the harvesting, I mean, the prescription variables and so on. And with 8 million variables for these decisions, you cannot, it will be very difficult to add, to incorporate this in a more complex model. So we are now trying to exploit this existing road cover to compose the problem. And I cannot point here, but we can see that here you have pink. This is a map of Paiva region with the national roads, municipal roads, and management units that are either pink or green. Pink ones are the ones that are not crossed by a road, and the green ones are crossed by a road. And I mean, we can you can see. I cannot point, but you can see that some of these areas will be the pink ones. For sure, will send the wood to a road surrounding the area, and the green ones can send the wood to either one side of the road, either the other side, or to the road itself. I mean, to this road. So actually, the wood is not going to be sent very far from each management unit. It can be sent very far, but you can control the area. And you already tried to use it to reduce the bounds in the first formulation, but we are not very successful. Instead of 7%, we could have 5% gap in 24 hours. But we believe this is the way to go. I mean, we have other ideas to compose the problem using this existing road cover. And that's it.
Thank you.
Thank you very much.
Good afternoon to everyone. Are you listening? Are you listening? Okay, thank you. So good afternoon. My name is Liliana Ferreira. I'm going to talk about the introduction of spatial optimization concerns into forest ecosystem management decision problems. Lately, I have worked more closely with my colleague Alexandra Batista, also from the Polytechnic of the Institute of Leiria, but we also have had some collaborations of several researchers that also collaborate in this Bioecosys project. Sorry, this was too fast. Okay, the case study is the same, so I'll just summarize it and then I'll show you the MIP model that we have been developed. So we are also using here the ZIF of Val do Sousa as the case study area. As it was said before, it encompasses these three counties, Paredes, Penafiel and Castelo de Paiva. Paredes is the smallest one and has only pure stands, while Paiva is the biggest one and encompasses both pure and mixed stands. So to this forest, we wanted to develop a landscape level management model that could help us to find a policy to be adopted by the stands that compose that forest. We wanted to ensure a more resistant forest to wildfire and also to limit the contiguous clear cut at the same period. We also had some concerns about timber volume regularity. And after defining the decision space the stakeholders can introduce the model into the F-goal model, as Suzette explained before, and do their trade-off analysis in a multi-criteria analysis. So as we are working here in a forest ecosystem framework, we will compute in our solutions the indicators for the different products and services that were considered here. Specifically here, we have used the adjusted wildfire resistance index that considers, I need to point, not only the specific resistance of each stand, but also a correction term that takes into account the resistance of the neighbors. So this correction term considers aspects as the common border, the relative position, the existence of paths, and also the shape and dimension of the stands. Our decision variables are also binary in our model and assume the value 1 if the stand height is managed according with the prescription G, and if it is chosen a pre-DCP for shrub cleaning. Of course, we have different sets of prescriptions for different stands. In a first approach, our model was defined by the following equations. Here we can have different objective functions, we can change them. Then we have the constraint that guarantees there is chosen one prescription for each stand of the forest. The constraints related with the regularity of volume for the different periods of the planning horizon, and the restrictions related with the wildfire resistance, where we try here to guarantee a minimum average value for wildfire resistance in each period. Then we have the equations that will compute the value for the different products and services of this ecosystem. Oh, sorry. We didn't solve the problem for the whole region together. So we have here just some preliminary results for Paredes when we use different objective functions. For instance, when maximizing the total net present value, the total volume, considering or not here a minimum level for the resistance in each period. Here we are using a variability of volume of 10%. And we can see that there are many differences in the solution, namely in what concerns to the net present value. When we demand a minimal value for the wildfire resistance, the impact is huge, but I think we all have to be aware that to have a more resistant forest, we have to assume some costs related with prevention actions. But of course, these are extreme solutions, extreme points, and we also could balance this. For instance, limiting the losses of the landowners, if we included into our model constraint to guarantee, for instance, a minimal value for the net present value. For Paredes, we didn't have problems to solve the problem. It ran fast. Here, just an image where we can compare what is obvious when we try to maximize the net present value without concerns related with wildfire resistance. We will reach a much more vulnerable forest to wildfire, comparing with the scenario where we try to maximize the wildfire resistance. Afterwards, we tried to introduce another environmental concern related with the harvest activity. And as Isabel has mentioned, when we have a contiguous area that is clear-cut, we have some problems for adjacent stands. So in this research work, we defined a limit for clear-cut area in the same period that was equal to 50 hectares. We use here the path formulation also mentioned by Isabel and used by her before. So we are going to consider here the clusters that are contiguous set of different stands. And we say that have an unfeasible cluster if the total area of that cluster is greater than the maximum area that is defined as the limit area to be clear cut in each period. And then we have a minimal unfeasible cluster if for each stand that compose the cluster, when we remove it, the resulting cluster or clusters are already feasible. For periods, when we address these adjacency constraints, we had to define new binary variables, this y high t equal to 1 if the stand high is completely harvested in period t and 0 otherwise. And then here we had this cover constraints that guarantee that the total number of clear cuts in all the stands that belong to the minimal and feasible cluster are less or equal to the total number of the clusters that belong to that minimal and feasible cluster. Unfortunately, when we had these constraints to the model, we didn't get a solution for all the stands. Sorry. For instance, here, just the results for periods without adjacency constraint, an example when we try to maximize the volume in the second period, we can see here this huge pink area, contiguous area that is clear cut. But when we have the adjacency constraints, that does not happen anymore. It's not very clear, but there are green stands here in the right and yellow stands. We cannot see them very well, but the green stands do not consider it harvest, and the yellow stands are the stands for which we don't have solution. And we don't have solution because in our data set, there are prescriptions that have mandatory clear cuts for the same periods for those stands that compose the same minimal and feasible clusters. So it's impossible to satisfy these adjacency constraints. Of course, we can overcome this problem if we consider new prescriptions with some lags in these clear cuts for these stands. One step forward, we tried to solve the problem to Castelo Paiva, but the problem became much more difficult because it's a bigger area, we have more stands, and also because the number of minimal and feasible clusters has increased significantly. For Paiva, we have more than 40,000 of minimal and feasible clusters, so much more constraints to satisfy. Another detail is that in Paiva, we also have 62 mixed stands. These stands are divided, so part of the stand, part of the area of the stand is allocated to one species, and the other part is managed according with other species. So in fact, they are managed as independent stands. But when we are working with adjacency constraints, they are seen as a single stand. I'm seeing I have here some problems with the symbols here. For instance, when we have a management unity that is a mixed stand, we have to consider that unit in the set of all stands as set, but we also have to take into account these two divisions in the other set I that consider all the stands and the divisions of those mixed stands. To address the adjacency constraints in the Castelo Paiva in this model, we had to develop new binary variables, these ZST, that are equal to 1 if the stand S is completely harvested in period T. And these Z variables are only equal to 1 for mixed stands if the two parts of the stand are clear cut at the same period. So to guarantee that, we had to address this equation into the model, and then the constraints, the similar constraints that we had already used for periods in this case. Again, we didn't find a solution for all the stands. And we have here some examples of solutions to PIVA. Without adjacency constraints, we only could have the solution with 35% to regularity of volume variation. We have the similar trend that we had to Pareto when we maximize the total net present value or when we maximize the resistance of the forest. And we could solve this problem under 10 minutes, I guess. Yes, 10 minutes. With the adjacency constraints, it was much more difficult to solve it. We didn't get a solution for all the management units, as I said before. We tried to consider 50% on regularity of volume and 40% of regularity of volume. These are fresh solutions. We only could achieve them yesterday after having all the minimal and feasible clusters. Of course, this took much more time. Here we solved the problem just under 1 hour, and here it took 1 hour and a half, more or less. Sorry, I'm just finishing. Here, just some images of our solutions. Well, we can see for these 2 periods that we cannot find big pink areas that are where are the contiguous harvests. So we think our model is satisfying the adjacency constraints. However, there are still those yellow stands for which the model didn't find a solution. As it was said at the beginning, after solving the model, it can be introduced in the FCO model, as Suzette showed before, and then the stakeholders can choose the optimization functions that they want to optimize and visualize the criteria space and choose the best options for them. So, as a conclusion, I think we think that our approach provides a forest ecosystem management model that tries to bring together some spatial optimization concerns, namely the wildfire resistance and the contiguous clear-cut area, the limitation for contiguous clear-cut area. And additionally, it also enables the stakeholders to have a multi-criteria analysis in a multi-criteria space afterwards. So this is it. Thank you.
So I want to thank all the speakers that did presentations this afternoon. So the session is very long, but let's, if we stop now, we won't come back. So now we will have the session for Q&A questions for all these 7 presentations. So I checked the chat on YouTube, so we have some questions for the speakers. So Brigitte and Miguel, well, they won't fit in the table. So if we have questions for them, I'm sorry, if we have questions for them, I will ask them or to speak in the microphone and near the microphones for the streaming, so the people at home can hear the questions. So let's start first with the questions in the chat, and then we move to the questions in the room, if you don't mind. So I have a question here, probably for Brigitte. It's from Tiago Lima. He says, is the biodiversity index including grazing animals? I'd imagine more diversity herbivores would lead to a higher fire resistance with compromise on wood harvest. I think this question is more for Brigitte. Brigitte, can you?
Good afternoon. Thank you for the question, Tiago. Actually, for the biodiversity score, we are not including the fauna information. We are using the information from the forest inventory, so we are using the forestry composition and also the shrub. And we are including the age and rotation. However, this biodiversity score is a surrogate for biodiversity, and you are assigning a mean and a maximum scores for the forest species, and you believe that they are related to the fauna. But it's the next step. We want to build that bridge between the flora and fauna information. Thank you, Kim.
Thank you. So the next question probably for you or even or for me, but it's from Kevin. Did you ever try to consider the steeper slopes during harvesting operation and their impacts on soil erosion?
Kevin, thank you for the question. Actually, our rules equation already included the information from the slope. We have the factor LC is already including the information. So yes, we can say that we have we join all the information from the rules equation and we innovate in the C factor that now is dynamic. Not as thank you.
So another question from Kevin, but now to Eduardo Eloy. So Kevin is asking you, did you ever try to capture how forest site productivity may affect your model in wood yield and in different management units?
So if how productive were management units and if that affected the solution? No, we just had the prescriptions which told us exactly, supposedly, how much each prescription would yield in each management unit. So we didn't have that information.
Another question, sorry for you again, Eduardo. So decision about what species to grow, how intensively to manage the trees, or whether or not trees are the best crop for a particular piece of ground, are all tied to how plants grow on a site. Trees grow in a very productive site may be thin more frequently over a rotation than trees growing on a less productive site. Well, I think it's more or less related to the previous question.
It's related to the prescriptions. In the project, we got the prescriptions from another project. So that's, I didn't know about that, but thank you for that information.
Okay. So this is more a question, so someone is asking if the presentation will be available for the participants. I would say yes, in the website. After the conference, we will put there the PDF presentations, so they will be available. So the last question in the YouTube chat is for Liliana Ferreira. Did you consider the fire causes, probability of fires to occur, and the different type of fuels in the management units?
Yes, in the wildfire resistance, there are the specific resistance is computed according with damage models and probability wildfire models, and that is taken into account in those models.
Okay, thank you. So I think there are no more questions in the streaming. So any questions? Anyone wants to add something to the questions that were already done? Everything was clear to everybody? If yes, it's excellent. It means that we did a good job. Or even people that is still on Zoom. Brigitte, por favor, só de Jens tem. So we have a question here in the room from Jens.
less time, but include a lot of intervening forced movements. And I didn't really understand how you exactly, I don't know what you at all exactly the planning process, all these one control or something for the and how are you calculating the reservation price and how was that actually done? And do you know if the forest owners, if you use the current model to calculate the reservation price, do the forest owners accept this reservation price or these different management plans?
I think, Miguel, can you, the question is more about reserve prices, how they were. Miguel here.
Yeah, for the reserve prices.
Miguel, do you mind coming here next to the steering microphone? It's easier for people.
Sorry.
So, yeah, but I think it's quite a steady and maybe if I closer to you. There is a lot of forest owners and you have some reservation prices for different plants. And the reservation price you have for different plants when you sow tilling, this must be an aggregation of the reservation price for all the forest owners that have been different. We had one of the reservation price is associated to a particular and the reason is that the supplier here is a collective forest owner. So they are represented by the Association of Forest Owners and they collectively offer.
Any other questions? No? So it means that everybody here was very clear and the audience perfectly understood hard research work that we have been developing in this project. So I don't know if there is no more questions. We are getting late, so it's 10 to 5. Shall we move to the other room to have our coffee and have the ending session there? So thank you, speakers that are here and all that did the presentations. Thank you very much, and thank you for the questions also. Thank you. Attended the sessions. If you want to wait a little bit, we will have the session, World Cafe, and then the closing session. I think Harold is raising hand. You want to say something, Harold?
I was clapping.
I was clapping. Oh, sorry. Looked like a raising hand, sorry. But thank you for your nice presentations this morning.
Thank you.
Thank you very much. So see you in 10 minutes for the closing session. So the people that it's here, let's move to the phone over, please. Thank you. Yeah. Ai, não vi, não.
Right. Okay, so please, your attention. So thank you for being present in this final session. As we mentioned earlier, this morning, we were developing research with a case study, a living lab that supported all our research activities. We are very much concerned with this bridging of the gap between science and practice. And so in this final session, we'll have some remarks and some closing words by the leader of the Forest Owners Val do Sousa Association, which helped develop this research and with whom we have worked over these 3 years. So I would give now the floor to my colleague, Professor Américo Mendes, the president of the Val do Sousa Forest Owners Association. So thank you, Américo, for being available to be present in this final session and for your closing words. I give you now the floor.
Hello, everyone. Thank you very much, Professor José Guilherme Borges, for this opportunity.
Do you have your micro active?
Yes, I have my micro on. Can you hear me? Yes? Can you hear me? I can hear you, but
yes.
You can hear me.
It works on Zoom, but maybe not.
Yes. Can you hear me now? Oh.
We don't hear you, Américo. Can you say something for us to adjust the sound?
Can you hear? Can you hear me now?
Very badly.
No. Not yet.
Not yet.
Can you speak?
Can you hear me now?
Professor, if you could ask one of the other speakers, if you can ask one of the other speakers to talk, just to see if the issues on our side or
It's on his side.
on this side.
We hear you in the computer, but not on the. Yeah, we hear it here, but not in the. É isso?
Provavelmente.
Okay.
Um pouco mais.
Só tenta entrar. Okay.
Now, can you hear me?
Just a second.
I can hear you.
Not yet.
No?
Continua.
Então, baixo.
Não, que até devia estar a sair da televisão e não está.
Pois.
Estava a ver se este funcionava. A sair as colunas do computador e apontava-se aquele microfone para as colunas. Pois é, isso que eu estava a pensar.
Isto foi testado.
Sim. O quê?
Nós assistimos aqui pelo YouTube, se ele tem som, o YouTube está só a ouvir.
Não, o problema é que só está a sair aqui do computador, não está a sair, por exemplo, das colunas da televisão.
Ligamos aqui.
Can you speak to test?
Can you hear me now?
Yes, but in your laptop and not television. And now, can you talk?
Can you hear me now?
Yes. Yes.
So please go ahead, Merrick. Sorry for this trouble with the technology.
It's fine now?
Yeah, it's fine now.
Fine, okay. Okay, good evening, everyone. I'm very thankful to Professor Borges and his team for this opportunity to be here with you. If it's not for Zoom, I wouldn't be possible for me to participate in this conference. So as I told you, I'm speaking on behalf of the Forest Owners Association of the Sousa Valley, And in this brief presentation, I will just tell you very quickly who we are, where we come from, what we do, and present you some results of a study I was involved in some time ago, which I think are relevant for as a complement for the main topic of these projects. So I will share the slides I prepare for you. Let me just put them on the screen. So just okay. So the title I gave to this short presentation is "What's the value of forest ecosystem services in Portugal and what can we do about it?" First, just a very quick presentation about our association. So we are in the northwest of Portugal, for 40 kilometers east from Porto. We cover 6 municipalities in this region for a total forest area of 29,000 hectares. Our association so far has for almost 500 associates. They are most of them small-scale private forest owners, and we exist since 1994. So we are more than 25 years old. So this is just a picture of how forestry and the other landscape looks around here in this area. So we have small pieces of forest, houses, some forest land, some agricultural land in between. So this is the typical landscape from our region. What service do we provide to our members? So we represent interests of the members. We provide forest technical advice with one forest engineer. We have 2 teams of 5 forest subs each, which do preventive forestry works throughout the year. And we try to promote grouped forest management through forest intervention zones that we establish in our territory. So this is just a picture of one of our teams of forest suppers. As I've just said, we created 4 forest intervention zones, which is a way of promoting a grouped forest management in our territory. The results I'm going to present after this slide, they come all from a report that we just finished in last June, and which is an estimation of the total economic value of forest ecosystem services in Portugal. And let me go to the results that I want to present to you. In this graph, you have the top line is the total economic value of Portuguese forests, as we have estimated that in that study. It's about 2 billion euros per year. So it's the yellow line on the top. The brown line is the value of the marketable forest goods and services. The brown one is the non-market goods and services. You can see that there is this this bad year of 2017. As you might know, it was a very bad year in terms of very big forest fires in Portugal. And so this graph summarizes what's the share of the market forest goods and services and the share of non-market goods and services is more or less 50-50. So about 50%, about 1/2 of the total economic value of Portuguese forests is non-marketable forest goods and services, though. So it's a value that doesn't represent a revenue for the forest owners, but it's produced by our forests to the benefit of the whole society. in this graph, it's the value per hectare, the euros per hectare of the non-marketable forest goods and services. So you see it goes somewhere between 150 euros and almost 250 euros with this, again, with this very bad year of 2017. This graph is a disaggregation breakdown of the total economic value of forests by species. In our region, the main species are maritime pine and eucalyptus. So you should look to the brown bars in the graph, and you can see that for the conifers, the non-marketable goods and services represent a little bit above 50% of the total economic value of this type of forest. So more than half of the revenue coming out from our pine forests, which are still important in our regions, it's revenue that it's not revenue for the forest owners, but it's benefit for the whole society. Again, the value now of the non-marketable goods and services coming out from these different types of forests, and for again focusing our attention to the conifers, which are, as I said, it's still an important species in our region. The value of these non-marketable goods and services are about 250, 260, 270 euros per hectare. So what's the main implications that I would like to draw from these results? So as I've showed to you, about 1/2 of the total economic value of Portuguese forests corresponds to non-marketable goods and services. But since we are already for many years in a situation of negative private profitability of forests for many forest owners, the internalization of this non-market value is very much needed to reverse this situation. So this internalization can be done through the implementation of payment for environmental services schemes, which are still rare in Portugal. There are some more in the southern part of Portugal, not in this part of the country where we are. But they can also be done through the policy instrument that we have in our forest policy, which is called the Permanent Forest Fund, which currently has only about 3 million euros or even less than that. But this internalization, if it's carried out through payments to individual forest owners, and since our forest owners are very small side, these individual payments would not make a substantial difference. So if we give the amount of money that I've just showed to you, and if we think about the numbers for the maritime pine, it would be around 250 euros per hectare, and many forest owners they didn't even have 1 hectare of forest, so it's more than that. So this amount of money would not make any difference in their economic situation. So what should be done instead is that this internalization should be most of that should be done through support to grouped forest management, for example, by supporting the forest intervention zones like the 4 that we have established in our regions. And this grouping of small-scale forest owners is a public good, and is the most important public good that Forest Portugal needs right now. And this is instrumental for our forests to produce the other forest goods that we all know that they produce, like the environmental services. But if we don't produce this one before, we cannot have our forests doing well in terms of providing forest ecosystem services to the full potential that they could produce. But the support to group the forest management shouldn't be not only for investment that is needed in our forestry, but also for the functioning of this group, the forest management initiatives. And in Portuguese forest policy, most of the time the incentives have been to investment, but not to the functioning of the organizations that have to manage the forest investment afterwards. So we spend money in investment, and then since we don't invest or we don't support the functioning of the organizations that should help forest owners to manage their forests, then the fire comes and the investment goes away. So we need a change in our forest policy. So we hope that projects like this one can contribute to this very much needed change in our forest policy. And this is the main message I would like to leave to you. And thank you and congratulations for this very interesting conference. Thank you very much.
Okay, so thank you, Americo, for these closing words. We do need, as you mentioned, to promote landscape level management, joint management, support the organizations that are responsible for the joint management of forest areas in our country. In this project, that provided the rationale for all our work, come up with approaches that could help develop or support development of landscape level, joint landscape level management approaches as a way to provide the ecosystem services, and in turn get information and develop mechanisms that may promote the payment of those ecosystem services, so that that joint landscape level approach can be developed in fact. I would like to thank all speakers, namely from Austria, Germany, the US, Spain. So thank you, Harold. Thank you, Thomas, for being with us. And thank you for all the speakers and for the project, to all the project participants that have contributed to the success of this project. Thank you for the audience and for listening to us and you are interested in this topic. And last but not least, thank you for the organization committee, to Brigitte, Barbara, Suzette, who helped us develop all the logistics that was needed in order for the success of this conference. So thank you all, and hope we'll meet and continue this work and ongoing through novel project and other interaction and possibilities for interaction to contribute to the enhancement of decision-making in the forestry sector. So thank you all.
Many thanks, Jose.
Thank you.
Many thanks. Bye-bye.
Bye. Thank you. Bye-bye.